All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. We ended last class on an example. Let's actually get back to that. So let's make sure I can see everybody and see the chat. Okay, so last time we introduced the formula for conditional probability, and this was something like that guy. The probability that something happens given that something else already happened, right? So we looked at the probability that the sum we get when we roll 2 dice, given that I know one of the dice showed a 6, right? And this is something that we've looked at before in 2 flavors. We've looked at the probability that the sum is 10 before. And we can illustrate that from this table where we saw, come on, iPad. Don't understand why I have to do that. Okay. So we looked at the probability that the sum was 10 before with no restriction, right? So I roll a dice, 2 dice, there are 36 possibilities. What is the probability that the sum was 10? Well, I just had to count them, right? So I just went, oh, well, there's 1, there's 2, there's 3. The probability that the sum is 10 is 3 out of 36. Which is 1 out of 12. All right, so now let's look at a different problem. The probability that the sum is 10, given that I know 1 shows a 6. Well, if one of the dice shows a 6, then what that means is now only this row and this row are now in play, because in the bottom row, the last row or the last column are in play. Because in the last row, the second die would show a 6, and in the last column, the first die would show a 6. And I know that at least one of them have to show a 6, which means now, automatically, none of the other numbers are in play. None of the other possibilities can work. So essentially, I have to ignore all of these guys. Most notably, I have to ignore one of the 10s that I got before. So what we end up with is, well, this basically means that shading is not in sample space anymore. Right? So now the total number of possibilities is greatly reduced. So now I can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possibilities. So now it's not 36 things anymore because I was told something that put a condition on the probability that I wanted to find. And now what happens is essentially that condition reduced my sample space to these 11 points. And now I want to pick how many ways can I get 10? This way or that way? And I don't know. Geez, I don't even know how I would do that on the. Okay, I think that's not. Okay. Undo. Maybe I want to put this in a different color, but make that a little thicker. So, all right. Okay. So now the new sample space is 11, right? And so now when I want the probability of getting a sum of 10, given that I know 1 has to show a 6, well, now that's a little bit different, isn't it? That's going to be the probability sum is 10, given 1 showed 6. Well, that's now going to be, well, 2 out of 11, which is different from the 1 over 12 that we got before. In fact, it's now more likely that we would get a 10. Right? So now, yeah. So this was where we left off last time. And this was the answer that we got last time, by the way. So last time we did this, we got 2 over 11 as the answer. It's right there. Right? And we use that as an excuse to develop this new formula, which we call the conditional probability formula. And it's the probability of A given B. It turns out that it's going to be the intersection of A and B over the probability of A. And as you can see here, the 10s that I have in the second situation are in fact overlapping with the 10s that I had in the previous situation. It's just that I need them to intersect with the set B, which is what I have highlighted in yellow. Okay, so the yellow is like the yellow represents set B. Okay, now I find the intersection of set A, green represents set A, right? And all the numbers present represent the sample space, the sample points in the sample space. So now I kind of have that situation on my hands. So we saw, so the probability that the sum is 10, given that 1 shows 6. Well, this is going to be the probability that the sum is 10, and at the same time, 1 shows 6. Right? Which is, you can see over here. Right? So the sum is 10 and 1 shows 6. Divided by the probability that 1 shows 6. Which in the top case would be 2 out of 36, and in the bottom case would be 11 out of 36, which leads you to 2 over 11, which is the answer. Okay, so that was what we called a conditional probability. It's a probability that we found based on a condition. And we know it's the probability of A given B is the probability of A and B over the probability of B, right? So we derived that formula last time. So we're now caught up. So the idea is putting a condition on the giving a condition can potentially, not always, in fact, I'm going to talk about a way that it doesn't have to, that it won't, can potentially change the sample space and hence potentially change our probabilities. Okay, and this is something that, again, we saw with the 2 girls problem. Okay, a couple has 2 children. What's probably that they have 2 girls? It was one answer. What's probably that they had 2 girls if we know that the older child is a girl named Freuda, right? It gave another answer. what is the probability that if I know one is a girl, that this second one is a girl? Different answer, right? I put different conditions on it. And what we saw what happening was we were reducing the sample space and choosing out of different things, right? What is the probability that they have two girls if we know one is a girl born on a Monday? That changed it again, right? It changes the sample space, right? It doesn't have to though, but it can, right? So we saw this last time where this is read given, just to remind you, the language is important. And B, this is kind of like the condition. Event that is assumed to have occurred. And A is event, come on, iPad. Event we care about given B has occurred. Okay, and this guy was read as the probability of A given B. Okay, and I guess to remind you again, FASO select. This is equal to the probability A will occur given that B has already occurred. Okay, so that's very important. Okay, we can now talk about a very important concept. They're very important. Students often get them both mixed up, but that's because they're trying to rely on their intuition as opposed to the rules of probability that I'm giving you. Don't do that. You know better. So let's actually talk about those because that's very important. And we'll talk more about this as time goes on because these concepts will continue to creep up. So one of the things I want to talk about is the idea of independent events. Okay. What does it mean for two events to be independent? So we say events A, B are independent or are independent events. Right? If, and here's what independence means. One event occurring has no effect or no influence on the other one occurring. If they do not affect each other in the sense that one occurring has no bearing or influence over the other occurring. Right? So this is what's called, these events are, any such two events are called independent events. So if I flip a coin, fair coin, what is the probability that I get heads? Well, it's a half. All right, what if I told you that before that, this event happened? I took a standard deck and I drew an ace of spades. Now what is the probability that I would get heads? It's still a half. It's why would that change? Like that event over there, if you picking the cards, has nothing to do with flipping the coin. Like they're like, okay, that's not. So you picked an ace of spades. It doesn't matter. You could have picked a queen of clubs and it would still be a half, right? The probability of getting heads on a coin flip is independent of the card that you choose from a standard deck, right? One is not going to affect the other. It's not like you choosing the ace of spades now makes heads more likely or something like that. It's not going to happen. They don't affect each other, right? So that's what independent events are, okay? It's very important that we can identify independent events or dependent events, right? Because you want to know when finding probability, what are the things that can affect this probability? What are the things that don't affect this probability that I don't have to care about, right? Those are going to be some important ideas. In particular, let's actually get to a formula for this. A, B independent would mean knowing that B occurs or occurred would have no influence on A occurring. So if these are independent events, then I know if one happened, it doesn't really change the probability of the other one happening. On A occurring. And so what that means is the following. This means that the probability of A given B, given that B already happened, what is the probability of A is happening? Well, if they're independent, the probability is just going to be the same as it always was, right? The probability of A given B would be the probability of A when A, B are independent. Okay. So now, the thing is, we actually know a formula for the guy on the left. This guy we know is equal to the probability of A intersect B divided by the probability of B. So what this is actually saying is that, well, the probability of A intersect B over the probability of B must be equal to the probability of A if A, B are independent. And so what we get is that the probability of A and B must be equal to the product of the probabilities if A, B are independent. Here. Okay, so that is a very important equation. There were times in the past when we could get a probability by multiplying the probabilities, and then there were times that we could not, right? If you look at, I think this also occurred in the two girls problem. There were times when we could just multiply the probability. So the probability of getting two girls was a half times a half, right? Probably of getting a girl and then a probability of getting a girl. And we could multiply the probabilities, but there were other times when we multiplied probabilities. I don't remember an exact example right now, where if for both to occur and you take the product of one times the other, it didn't give you the answer. In fact, I'm going to do an example where that's not true pretty soon. And so there are times when multiplying the probabilities gave you the answer, and then there are times when it's not. So if you think I can always multiply the probabilities when an and shows up, and automatically translates as multiply, you are incorrect. And that is an intuition that a lot of people have. That, oh, because there's an and, I can change the multiplication and just multiply the probabilities. This is not true. This only works when the events are independent. And it's not going to work if they're not. So you can only do that if you know they're independent. So this leads to the following. A, B are independent if and only if. It's not that I can't spell the word if. That actually means if and only if. Meaning the implication goes both ways. If I know they're independent, what I'm going to say now is true. And if I know what I'm about to say now is true, it means that they're independent. It goes both ways. That's what that means. So they're independent if this happens. The probability of A given B is just the probability of A. If you notice that B occurring does not affect A occurring, they're independent. By symmetry, it of course happens the other way. The probability that B occurs given that A had occurred is just the probability of B occurring. Like A occurring had no effect. And then finally, the formula that we just derived, the probability of the intersection is the product of the probabilities. So the probability of A and B is the product of the probabilities of A and B. Okay. Knowing this, very important. Okay. This is what independence means. I do not want you to think about independence from this point on as some sort of concept or like, well, it just means one doesn't affect the other. What does it mean that one doesn't affect the other mathematically, right? It's a math class. So when you're talking about this stuff, you're not going to like try to reason with me about why something is independent. If I ask you to show that something is independent, what that means is I'm asking you to show that one of these three equations are true, right? Independent means this, right? This is what it means, right? For us, right? Everyone else can have their own interpretation of what independence means, but a lot of them would be wrong. Mathematically, this is what it means. And I think we've done enough for me to show you that probability and our intuitions don't line up often. So whatever your intuitions about what it means for one thing to be independent of another, that's cool. Don't allow that thought in math class though, because it doesn't work. Independence means one of these three equations are true, right? And they hold only if these equations hold only if A, B are independent. There's a reason that I'm harping on this, obviously, because it's very common for students to just be like, oh, probability of A and B, let me just multiply the probabilities. It's a very common thought, and it's incorrect. It's presumptuous. It's premature. Like you can only do that if you know they're independent. If you don't have any reason to believe they're independent, you cannot do that. Okay. All right. There's another very important kind of event that we want to talk about. Dos. Remember that one? Okay, yes. And this one is actually often mixed up with independence somehow. And that's because students are relying on their intuition as opposed to the math. You guys know better now, I'm telling you. So the idea is something called mutually exclusive events. Another way, they're called sometimes, not very often. Usually we use the phrase mutually exclusive, but AKA it's disjoint events. Okay. So we say A, B are mutually exclusive or disjoint events if they cannot occur at the same time. Or they cannot occur together. Let's write it that way. Cannot occur together. Okay. I.e., the probability of their intersection is 0. Okay. Now, this happens precisely when the events are disjoint. This happens precisely when the events are disjoint. And you might recall A-B disjoint means the intersection of A and B is the empty set. And so if disjoint, that would mean that the probability of the intersection is just the probability of the empty set, which is just going to be the size of the empty set over the size of the subspace, which is 0. Okay. So that's what we get. This is why it's also called disjoint events, but we usually call it mutually exclusive. They mutually exclude, one mutually excludes the other. So if this one occurs, it excludes the other one from occurring. And if this one occurs, it excludes the other one from occurring. They cannot occur together, right? So this is true. If A, B are mutually exclusive. Someone's coming in here. Okay. Now, I also want you to recall something. Also, recall the law of disjunction. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A intersect B. Now, if A, B are mutually exclusive, i.e. disjoint, then the probability of A and B is 0. And so this would mean that the probability of the union is just the sum of the probabilities. Because now the subtraction part is 0. You're subtracting 0. This also follows from the third axiom. Okay. So we get the following. A, B are mutually exclusive if and only if, right? One of these equations are true. The probability of A intersect B is 0, and the probability of A union B is the probability of A plus the probability of B. In other words, the probability of A or B is the sum of the probabilities. And we saw this in counting, right? When we didn't have overlaps and we wanted to find the total number of ways to count something, we actually just counted the total number of ways for one thing, the total number of ways for the other thing, and then we added them together. So because probability amounts to counting stuff and then dividing by something, that the same thing would apply. So if A and B are disjoint, they're separate things, they do not overlap, then counting the number of ways that this thing can happen, then dividing by the size of the sample, then counting the number of ways this thing can happen, dividing by the size of the sample, and then I would add them, you get the probabilities, right? So that is true. Okay, so mutually exclusive just means they cannot occur together, right? And I do want you to realize that these equations hold only if A, B are mutually exclusive. Okay. Now, here's the thing. Here's how students can get messed up. Because they would say to themselves, well, if they can occur at the same time, that means they're kind of separate. This means that one does not affect the other, and that also means they're independent. No, it doesn't. That's not what it means. Mutually exclusive means these equations are true. That's what it means. The moment you start reasoning to yourself and using your own intuition, the chances are very high that you're going to be wrong, right? It's just the nature of probability. The human brain was not built for probability. Human brain was built for other types of calculations. So now that's what it means to be mutually exclusive. So if I asked you, are these two events mutually exclusive? You are not to try to explain this to me. What you're going to show me is that one of these two equations are true. And are they independent? You're not going to try to explain to me in words. What you're going to do is you're going to show me that one of these equations are true. And that is what that means to us, right? That is how we have to think about probabilities in terms of these rules and equations, because our intuition will lead us astray. I think we've done enough examples to kind of show that. Let's actually do another example to hit these home. To probability set one, I added a couple problems. I don't remember if I've uploaded these to the class yet, but I guess to the class webpage yet, but I think I'll do that later. Let's do problem 9. Problem 10, we are going to do next time, because that's going to segue into another topic, another formula I want to tell you guys about. Okay. So get the scaling right here. So I don't do that thing where I'm like writing in a different size in different parts of the page. You have all 4 aces taken out of a standard deck. You shuffle them and pick 2 at random. Let A be the event that the ace of spades and the ace of clubs are chosen. B is the event that the ace of spades is chosen. Are A and B independent? Justify. I guess we can also do are A, B mutually exclusive? Why not do that while we're here? I gave you the definition for both. All right, so let's actually get through this. What we can notice is that we have a set of 4 cards, namely ace of spades, ace of clubs, ace of hearts, ace of diamonds, right? So this is spades, clubs, hearts, diamonds. Okay. Now, suppose we don't care about order. And we know repeats won't occur. So once you make that decision, remember, this is how we're going to do probability. You're going to go into a problem and you're going to decide, do I want to think about this in a way that order matters or order doesn't matter? It's one of the first choices you make. Because once you make that choice, it automatically tells you how you want to build your sample space and what counting techniques apply. This means we want to choose subsets of size 2 from the above set of size 4. Now, what that means is I am now thinking of my sample space as a set of sets. It's the set of, say, I get the ace of spades and the ace of clubs, or let's say I get the ace of diamonds and the ace of hearts, or I get whatever, right? I'm just getting a set of 2 cards. No repeats, and I don't care about the order. But this automatically means I can find the size of S via combinations. 4 choose 2 will be the number of possible ways that this can occur. So that's 4 times 3 over 2 times 1, which is 6. There's 6 total ways, 6 total possibilities. If I were to write out all the members of S, which I don't want to have to do, I would have 6 of them. So now, also, we know that A is also a set, right? A is going to be the set that A is the event that we get ace of spades and ace of clubs. So this is a subset of that set. So this is the ace of spades and the ace of clubs. Right? And B is the set that the ace of spades is selected. So I know that my ace of spades needs to be one of the selections. So I can get an ace of spades and an ace of clubs. I can also get an ace of spades and an ace of hearts. I can also get an ace of spades or an ace of diamonds, and that's it, right? So notice then that the size of A is 1 and the size of B is 3. All right, so now let's actually talk about independence. Okay. So independence means to show that they're independent, I'm going to have to find all these probabilities and then kind of figure out what must happen. So let's start by finding the probabilities of A and B. Note, the probability of A is going to be the size of A over the size of the sample space. We saw that the size of A was 1, the size of the sample space was 6. Okay, cool. The probability of B is the size of B over the size of the sample space. The size of B was 3, right? We have that up here. Size of the sample space is 6, so that guy's a half. Also, if I were to find the probability of A and B, this is the size of A intersect with B over the size of S. Okay. Okay, so now make sure that you guys are actually paying attention, listening to me. Who can tell me what is A intersect B? these two sets? What is the intersection of these two?
Is it ace of spades and ace of clubs?
Yeah, it's just that one set, right? So that leads us to 1/6. So now what you can do is you can check. Is the probability of A intersect B, which I know is 1/6, is that equal to, question mark, the probability of A times the probability of B? Probability of A is 1/6. The probability of B is 1/2. This is 1/12. So guess what? No, they're not the same. This means that the probability of A intersect B is not the same. Maybe I should put that as the probability of A times the probability of B. And therefore, A, B are not independent. Because that equation is not true. You can also notice that this makes sense, since if told B occurred, then the sample space changes. It changes size from 6 to 3, right? Because B only had 3 possibilities. So if I told you B happened, it means there are only 3 possibilities. And A is in both. Is completely contained in both. So the numerator doesn't change in the probability, but the denominator does. So this means that the probability of A given B is now 1/3, which you would notice is not equal to just the probability of A by itself, which we calculated as 1/6. Also, if told A occurred, sample space shrinks to size 1. Right? Namely, it becomes the ace of spades, ace of clubs. And this one element satisfies B, right? Because the ace of spades is chosen. So this means that the probability that B will occur given that A occurred, well, it's 1. It's 1 out of 1. While the probability of B that we found earlier was 1/2, right? So I can also see that the conditional probabilities won't actually work out, right? So the probability of A given B is not the probability of A, and the probability of B given A is not the probability of B, right? To answer the question, are A and B mutually exclusive? What would you say based on our calculations here? Are they mutually exclusive? Yes or no, and why? What do you guys think? This is the last question, so just give me your answer, tell me what you think, and tell me why you think that, and we will go. And just to remind you, mutually exclusive means this is true. And yeah, we have these calculations. So what do you think? Anyone? Bueller? I mean, you guys are thinking something. So let me know what that is. Are you guys still alive? Is anyone out there? Guys away from your computer? Like washing the dishes or having breakfast or something, I don't know. like I can't tell, like no one has their camera on. I don't know what you guys are doing. But the answer is no. And the reason is the probability of the intersection we found is 1/6. And in particular, 1/6 is not 0. For A and B to be mutually exclusive, the probability of the intersection must be 0. The fact that it's not 0 means it's not mutually exclusive. So that is the answer. So just you seeing that the probability of the intersection was 1/6 tells you that it's not mutually exclusive. What I would like you guys to do for next class is try your hand at this problem. You can definitely do it by what I've taught you before. And I would kind of maybe even recommend a visual way. So do a tree diagram or a table or something like that. Try to figure out the answer. And then what we're going to do is we're going to come up with a formula that can describe these. But we'll do that together. If you can come up with a formula that you think based on your calculations, what you think a good formula would be, by all means, you can share it. But we will develop a formula together next time. And for now, we will end there. I'll leave this problem in the notes for you guys to try. And that's that. So hopefully that was clear. TGIF, have a good weekend, everyone, and I will see you guys in the next one.